Hello everybody, my name is Jamie Wibbe and I am a PhD student at the GRC group from the Technical University of Valencia. I would like to welcome you all to this talk. As the title suggests, I'm going to talk about providing resilience to the UEV swarms. First, I will give you our motivation for developing this protocol and talk about the problems that we are facing. I will then proceed by giving you an overview over what we did, how we tested it, and of course our results. And then finally, I will finish this presentation with the main conclusions and our ideas for future work. UAVs are and have been for some time a hot topic. We can see this in the many works that are produced and the attention from the media. Lately, the research is shifting more towards groups of UAVs, which we also call swarms. The reasons for that are very logical. First of all, our knowledge of UAVs is profound enough that we are now able to experiment with more difficult things, like the UAV swarms. Furthermore, we can also see the great potential that lies in having groups of UAVs working together. Overall, those applications with multiple UAVs are quite slim. Luckily, there are already some researchers and development teams working on that, but we still haven't reached mainstream adoption. Which is a pity because there are many applications where swarms can be useful. For instance, in agriculture, wildlife recordings, border surveillance, or even people monitoring during the COVID-19 pandemic. The reason why those applications aren't adopted yet is due to the many issues that still exist. Organizing a swarm of UAVs is very challenging. For instance, we need to develop takeoff and landing procedures. We need to decide if we are going to use a master-slave pattern, and if so, how to elect the master. Once that is established, we need to create protocols so that the swarms can follow missions. And those are only a small subset of the many challenges paired to the UAV swarms. We have worked on those topics before, and in this work we will enhance our capabilities. The protocol that we designed is called MUSCO, which stands for Mission-Based UAV Swarm Coordination Protocol. And on this slide, I have presented its main objectives. First of all, it should maintain a swarm in a stable formation while it is following a mission. As one might imagine, if the speed of the drones deviates slightly, then over the time, the swarms become disrupted. Therefore, it is necessary that we counteract this problem. Of course, the solution that we design cannot introduce a large delay. And finally, this protocol must be resilient for the loss of any UAV. So we developed this protocol in stages, and in our first version, we managed to maintain a stable flight without introducing noticeable delays. The protocol was based on a master-slave pattern, where slaves were sending messages to the master with the last waypoint that they have reached. In this version, the master waits at each waypoint until all slaves have reached it. And then it sends an order to the slaves to go to the next waypoint. This version works fine until any UAV fails. Since the master waits at each waypoint until all the slaves have reached it, the master will wait indefinitely once only one slave has failed. Likewise, if the master would fail, all the slaves would wait at the next waypoint in order to continue. In order to solve this problem, we came up with a new version of MUSCO. In this version, the state of each drone is saved. A drone can be either alive or failed. Since the drones are continuously sending messages, the absence of a message indicates that a drone has failed. Each drone keeps a list with the states of all the other drones, and when they arrive at a waypoint, they check this list and update the swarm. In most cases, no drone has failed and the flight can continue normally. In other cases, a slave might fail. If a slave fails, it is simply removed from the list, and thus the master will not wait for the failed drone and send the order to all the others to continue the flight. Of course, there also exists the possibility that a master failed. In that case, a new master should be chosen. The new master that is chosen is the one closest to the center to increase network connectivity. Once the new master is chosen, it will broadcast a message that he is the new master, so that all the slaves are notified. After that, the flight continues as normal. Before going over our results, I will introduce our own multi-UAV simulator RDSim. RDSim is available for free, and anybody who wants to use it or just take a look at it, the repository is on GitHub and the link towards it is shown on the bottom of the slide. RDSim has a lot of features, and I will just highlight a few of them. First of all, RDSim is able to simulate multiple UAVs at the same time. Secondly, protocols developed in RDSim can be transferred to real UAVs seamlessly. On the right, we have shown our main interface to give an impression about RDSim. As you can see, there are multiple UAVs performing a mission. RDSim also has a command line interface, which can be used to run multiple experiments automatically. In a lot of experiments, the same actions need to be performed, like for instance taking off, landing, and moving to a coordinate. All those actions are included in RDSim and the user can access them via an API. Furthermore, for every experiment, we log a bunch of data in different formats so that the user can see exactly what happened during the experiment. And lastly, it also allows the UAVs to communicate with each other. And the models that we have used for the communications are based on real experiments. In the first experiment, we validated the working of our protocol. As shown in this slide, a drone fails before the first waypoint, yet all the others can continue the mission, just as we intended. We tried this experiment in different forms, as shown on the right. We let some slave fails, or the master, or a variation of that. In total, we did 5 different experiments. Now, a second experiment, we tested the point of failure. As stated before, at each waypoint, the swarm will be updated and the failed drone will be removed. A drone is considered to be failed when no message has been received within the time to live value, which was set to 5 seconds. This means that the point where a drone fails will impact the delay introduced by our protocol. Therefore, we have measured the delay introduced by our protocol during the experiments. In general, the delay is short, and in the worst case, it is equal to the time to live value. This is because if a drone fails just at the waypoint, it means that the others will have to wait at the waypoint for those 5 seconds before they update the swarm and continue their flight. In the best case, however, the drones fail far away from the waypoint, and when the swarm arrives at the waypoint, they have already recognized that one drone failed and they can continue their mission directly. Of course, whenever we design a protocol, it is also important that we think about its scalability. For that reason, we have conducted an experiment with many drones to see how our protocol reacts. During that experiment, we measured the time that the UAVs were waiting at the waypoint. In the first case, we can see that even without any UAV failing, the swarm waits around 2 seconds at each waypoint. This is because during that time, the swarm is synchronizing. We can see by the difference between the orange and the green bar that scaling the swarm up to 100 drones does increase the waiting time only slightly. In the second scenario, we let 50% of the drones fail at the same waypoint. This is an unrealistic scenario, but we want to see how our protocol reacts on extreme situations. And as you can see, the wait time increases only slightly with a maximum of 4 seconds. In the last scenario, we let 10% of the drones fail at each waypoint, on the 3 waypoints. Therefore, the overall waiting time did increase, but is still small when compared to the time that those drones spent flying. So, in this work, we developed a way to maintain a swarm in a stable formation while it is following a mission. With the use of our protocol, the delays are small. Most of the time, the delay is almost 0. And in the worst case scenario, it can go up to only 5 seconds. We have also evaluated our protocol for scalability. And as shown in our experiments, the difference between 4 and 100 drones is hardly noticeable during the missions. Finally, the protocol that I presented today is resilient for the failure of any and multiple UAVs. I would like to thank you all for your attention, and if there are any questions, I'm happy to answer them.